Hello, everyone. Welcome to the session on analyzing complex data in biostatistics and public health. Our session ID is 19. We are from UTC 9 to 10. And I'm the chair of the session. My name is HYUN LEE from Seoul National University, South Korea. And we have 3 speakers from Korea. They will give talks on various topics in biostatistics and public health. And because we have 1 hour for 3 speakers, I would like to ask the speakers to give their talk in about 18 minutes so that we can have some time for questions afterward. So I will give the speaker a heads up by speaking when there are 2 minutes left. For audience, if you have any questions to the speakers, please leave a question in Q&A or chat window. So I will regularly check on it. Okay, so then let's start. Our first speaker is Professor JUNGSOON CHOI from Hanyang University, Seoul, Korea. So now I think she can share the screen and start to talk.
Hey, everyone can check the slide.
Yeah, we can.
Okay, hello everyone. I'm JUNGSOON CHOI from Hanyang University. Thank you, Dr. Im, for the invitations of the great conference. Well, today my topic is a Bayesian spatially clustered coefficient model with temporal structure for the hepatitis A data in Korea. It is a joint work with JUNGSOON Lee, my former student. Let's talk about the motivations of the study. Health and covariate data are collected across the space and time domains. It is in this situation, statistical model commonly assume the covariate effect on health outcomes are constant over space and time domain. However, covariate effect may change over the space and time. Especially, some sub-regions may have heterogeneous associations with other, and within a certain sub-region, homogeneous temporal structure may exist. Okay. Now, let's talk about the motivating data. We have monthly hepatitis A instance data in Korean covering 250 spatial units for 2020-2021 year. We have 24 months. We observed the spatial temporal variations in this data set, and based on the previous study, we also considered 5 covariate right here. We also checked just the number of the percentage having a just a 0 value. Here is just about 45% of monthly hepatitis A instance on each area have just a 0 value. The meaning to develop the just statistical model, we have to consider zero inflated model. Okay. Well, before we're gonna construct a statistical model, we just investigate the data first. Well, look at this map. Actually, we investigated correlations between hepatitis A case and average temperature, which is one of our covariate for each region for 24 months. If you guys just look at this map, we have some spatial variations of the correlations, and we also found some spatial cluster like here. In this spatial area, they have quite similar correlations value. Another reason gonna be just the same thing. Okay, we just found some spatial cluster having similar correlations value. Now, let's move to the next slide. We also just checked the time series plot of the correlations between hepatitis A and average temperature by 7 provinces. Some regions have the quite similar temporal structure right here, but the others have the quite different. Okay, So from these two EDA results, what we obtained here is, okay, we observed the associations between hepatitis A and average temperature have the spatial cluster structure and temporal structure within each cluster. So we consider the spatial clustering with temporal structure for the coefficient of average temperature. Okay. Well, there are several studies addressing such spatial temporal variations regression coefficient. Gang proposed the spatially clustered coefficient model, but she didn't assume that she just assumed the constant coefficient over the time. And Lee introduced just the testing-based approach for spatial temporal varying coefficient regression model. And my previous work also developed a spatially clustered coefficient model with a temporal structure, but my work did not address just the spatial compounding bias problem. Well, spatial compounding bias has this significant impact in the parameter estimation. Especially in this question, our main question is we try to estimate just the coefficient. The meaning we have to consider spatial compounding bias issue. So in this study, okay, we proposed spatially clustered coefficient model with temporal structure, as well as two-stage framework to reduce the spatial compounding bias issue. And in our proposed model, consider Bayesian hierarchical framework to explaining just the spatial temporal variations of our data set. Okay. Here, I'm just briefly introduced our proposed statistical model. We have just YIT notation. It's gonna be number of the case in the I space at the time t. And here's the bold X gonna be just a vector of the P covariate. And zeta IT gonna be binary variable presenting just a zero structure with a probability PIT. Basically, my observed number of the case gonna be follow the zero inflated Poisson model with P and lambda informations. Well, here is we have the alternative expressions using the Poisson and Bernoulli distributions right here. Well, my statistical model, actually the main key is we just separate coefficient estimations and space-time variations estimation. So in the first stage, well, I just only consider just the covariate informations only right here. In this model, we didn't consider just the space and time variation. Okay, just only included covariate information. And my main question is here's the coefficient beta IT, and this notation can represent it, okay, just variations over the time and space. Now, I'm just we just assumed it some structure for here's the beta IT. So this slide is going to be presented spatially clustered coefficient with temporal structure. The key idea is, okay, my coefficient beta IT can be presented with beta spatial cluster indicator CIT, CI, and T. Here's the CI gonna be just the spatial cluster indicator, and we just assumed that here's the capital C number of the spatial cluster. For each spatial cluster, we assumed that here's the coefficient has the temporal structure. So in the next line, here's the coefficient following just the AI1 structure. We can just consider different temporal structure too. So, well, within this formula, okay, here's the beta IT can be just, okay, just a finite spatial cluster, capital C, and temporal dependent structure. And now we assume here's the spatial cluster CI gonna be follow the categorical distributions with selection probability 2. And this QI can be functions of the lambda I CI, and this expression gonna be just to consider a normalized structure. Actually, another question is, do we consider spatially dependent structure to capture spatial cluster? That's to do that, we consider here's the mean of the log lambda ICI has the intrinsic prior, which can present the spatial dependent structure. Okay, well, after fitting this model, we initially obtained it. Here's the beta estimator as well as the mu IT estimations. Well, using this mu IT estimation, we calculating continuous type residual RIT. Okay, actually, up to this model, we did not consider any space and time variations in the mean structure. Okay, so my next part is gonna be, okay, well, we consider space-time variation structure in the residual right here. So, well, we model here's the residual RIT hat gonna be follow the normal distributions, and mean structure gonna be just functions of spatially correlated, spatially uncorrelated, temporally correlated, temporally uncorrelated, and space-time interaction time. The meaning is that in this part, I'm just impose the space-time variations in this residual. Once we're gonna fit this model, and we actually obtained it estimated space-time variations as TIT have. Okay, well, actually, in the previous slide here, we obtained the initial beta estimator. And using the residual, we also obtained the estimations of the space-time variation. Okay, next, in the second stage, well, we just quickly plug in. Here's the estimated space-time variation term STIT hat. Okay, once we're gonna plug in this ST hat, and we estimated our interest. Here's the beta parameter again, based on zero inflated Poisson regression model. Okay, so we're gonna update it. Here's the coefficient parameter term. Okay, this is our main questions. Well, in this statistical inference, we use the Bayesian inference, and we use the non-informative prior distributions or the parameter. And MCMC sampling gonna be considered using the Nimble package. And well, here we have this CI gonna be spatial cluster indicator. That spatial cluster indicator parameter gonna be estimated using the posterior mode, and the other parameter gonna be estimated using their posterior means. Well, to evaluate it, just the model performance, we consider several measures, just the mean absolute error, mean square prediction error, the DIC, and marginal prediction likelihood. Well, to comparing to performance, to just evaluate just the proposed model, we consider just the 7 different competing model right here. Basically, we want to evaluate, okay, just how well the two-stage structure gonna be just working well, or spatial clustering of the coefficient, or temporal structure work well. And so I'm just set up here's the 7 model right here, and our proposed model gonna be indicated just model A. Okay, my proposed model consider two-stage model to reduce the spatial compounding bias and spatial cluster structure of the coefficient with temporal structure right here. Okay. Well, this is just the result of in terms of the goodness of fit measure. Well, in this situation, we don't know true number of the clusters. So we fit the model with a different number of the cluster from 1 to 5. If you guys just look at this table, we obtained our proposed model MA, model 8 with 2 clusters provided smallest MAE, MSPE, and DIC, and the largest MPL value. So from this goodness fit measure result provided, our proposed model has the quite good performance, especially with the 2 clusters. Okay. Well, so now we just investigated our best model, I mean our proposed model with 2 clusters. This slide, they're gonna be just to show that just the estimated cluster map. Okay. Well, everyone remember just our EDA map. So, the correlation map shows, and this area has the quite similar correlations values. So our estimated cluster just capture just the same cluster right here. Okay. So this map just presented two cluster, estimated cluster map right here. And we also presented, this is just the estimated temporal coefficient of average temperature for 2 different cluster. If you guys look at this temporal this plot, we can figure out, okay, these 2 temporal structure are gonna be quite different for 2 cluster. Okay, well, this is just a result of the parameter estimations of the alpha and remaining beta value here. I think it's I'm so fast here, so I'm just to summarize our talk. So, well, we just consider two-stage model as well as just the spatially clustered regression model with temporal structure. Okay, so from this data analysis result presented, okay, our two-stage model reduced the spatial compounding bias issue, and we also obtained just the proposed model with 2 clusters provide a really good performance. So, well, so summarize my proposed model just to allow the illustrating time profile within each spatial cluster of the risk impact, as well as reduce the spatial compounding bias issue during the estimating process. So this is just a list of the reference and funding informations. And thank you. Any question?
Thanks for the presentation. And I didn't notify you because you're on time. So thanks for the nice presentation. And I'm wondering whether we have a question from the audience. So I don't see anything in the message or the Q&A. So maybe then we will move on to the next speaker. There's one question actually from the chatting window. So did you encounter any computational issue when implementing Bayesian model? If so, how did you address them? That was the question.
Well, in this situation, we have just one computation issue just to getting the posterior sample, because it's kind of just a labeling of the spatial cluster index information. So to solve this problem, we just only consider single chain, just a long single chain sampling. Yeah. So this approach is gonna be quite works to gather just the unique spatial clustering index information. I think that's all.
Okay, thank you. Okay, now then we'll move on to the second speaker. Second speaker is Professor Ji-hyun Lee. She's from Yonsei University, Seoul, Korea. Now you can have your talk now. Thank you.
Thank you, Professor Lim, for organizing the session and inviting me for a talk. I guess everyone can see my screen right now.
Yes. Yeah.
Thank you. Hi, everyone. My name is Ji-hyun Lee. I'm from Yonsei University in Seoul, South Korea. Today, I'd like to talk about estimating time-varying treatment effects on restricted mean survival time in large patient database. I'd like to start by giving you a brief overview of this talk. The goal was to develop a clinically interpretable model to assess treatment effects on survival in large patient databases. Given that the restricted mean survival time, RMST, has attracted substantial attention already as a clinically meaningful metric recently, we have decided to build a model based on RMST. There has been several models developed based on RMST. However, with our problems of having a heterogeneous population of patients and where there exists substantial difference in factors between treatment arms and the possibility of having treatment effects changing over time, we couldn't really find the right existing method that were available directly. Hence, we propose a flexible model that estimates the time-varying effects on RMST by adjusting for the propensity scores. I'll begin by introducing existing models based on RMST and introduce our proposed model. Then I'll explain the estimating procedure. I'll present a part of our simulation results demonstrating the performance of the proposed method, and then illustrate the application of the method using real data example. I'll conclude my talk with some remarks. The hazard ratio is one of the most widely used measures in clinical studies to quantify treatment effects on survival. Cox regression, which is often used to estimate the hazard ratio, assumes that the ratio of the hazards between the treatment and control group remains constant over time. That is the proportional hazard assumption. In reality, however, this assumption might not always hold. And when this is violated, the interpretation of hazard ratio becomes obscure. Furthermore, the hazard ratio may be difficult to interpret in clinical settings. The hazard ratio, which is a measure summarizing the relative hazard of an event occurring at a given time for the treatment group compared to the control, doesn't directly translate to tangible outcomes, such as how many more days or months a patient might live with the treatment. Let's say we have an estimated HR, the hazard ratio of 0.7, but this doesn't easily tell whether that reduction is meaningful in practice. For example, a 30% reduction in risk might sound significant, but without knowing the baseline risk, it's hard to interpret whether it will meaningfully affect patients' outcomes. In contrast, the RMST, the restricted mean survival time, which is defined as the expected survival time with a restriction time point tau, has a clinically meaningful interpretation. The RMST can be easily evaluated by the area under the survival curve. And if we assume that the estimated RMST is equal to 2.7, we can interpret it as patients surviving for 2.7 years on average, which is a lot easier for clinicians and patients to understand and apply to decision-making. We can use either the difference or ratio in RMST to quantify the treatment effects. Now, let me introduce some existing models on RMST. The earlier model was focusing on estimating the RMST based on Cox regression model. it still assumes the proportional hazard assumption, so it's different from what we're trying to avoid. But based on the proportional hazard assumption, the Cox regression model, it requires several steps to estimate the RMST. And the disadvantage of using this model is the fact that covariate effects on the RMST cannot be directly estimated. Later on, in Tian et al. 2014 and Wang and Xiaobel in 2018, they proposed a direct model of RMST using generalized linear model. The model has this form where the RMST prefixed at tau is directly related to this covariate and the known parameter, the linear combination of them, through a lean function eta, which is a smooth, strictly increasing function. Within this model, we're interested in estimating this unknown parameter beta, which is also prefixed at tau, the restriction time point. And here, x tilde, the vector, includes ones for intercept and x for the baseline covariance. The estimating equations are constructed based on the IPCW approach. Now, as I mentioned earlier, we're interested in allowing the covariate effect to vary across time. Recently, Zhong and Xiaobel in 2020 has proposed this model where the treatment effects may vary across time. The model is slightly different from the previous version, where this is the restricted mean survival time, but now is not prefixed at a certain time point tau, but instead they allow this covariate effect beta tau to vary across tau by modeling it as a function of tau. So we decided to adopt this model and extend it to account for the fact that there may be substantial difference in patients' characteristics between treatment arms. We estimate the treatment effect by adjusting for the propensity score. Let me introduce some notations. T0 is the duration from disease diagnosis to failure. Z is the treatment indicator. X denotes the baseline covariance. And C denotes the duration from disease diagnosis to sensory. Then the observed data consists of T, delta, Z, and X, where T is the minimum of the duration from disease diagnosis to failure and the censoring time, and delta is the event indicator. We assume that C, the censoring time, is independent of the survival time, Z, the treatment indicator, X, the baseline covariance, and has a survival function that is denoted by G dot. The final proposed model has this form where we have two components. The first one is for the propensity score, where we're assuming the logistic regression model, where alpha is the unknown regression coefficient. The second component is for the RMST model, where we're adopting similar models from Zhong and Xiaobel, but here you can notice that V is now a vector of ones for the intercept, Z for the treatment indicator, and we also include the propensity score that was computed earlier. To model beta T, which is allowed to vary across time, we assume a flexible parametric function of time. We adopt the general m-degree fractional polynomials for modeling beta T. The m-degree fractional polynomials is widely known to be flexible enough to capture patterns that we can easily encounter in practice. And that is the reason why we decided to adopt this flexible parametric function. Beta T is gamma naught plus the linear combination of the unknown parameters gammas and the real value fractional powers of T terms. So the proposed RMST model can be rewritten adopting this m-degree fractional polynomial model by leaving the unknown parameters as a vector and moving all the time-dependent components into this covariate matrix where it becomes the restriction time-dependent covariates. We adopt the single estimation approach, where we first construct the estimating equation for the propensity score estimation to estimate alpha, the unknown coefficient from the propensity score estimation. that assumes the logistic regression model. Now, let me introduce some additional notation to introduce the second estimating equation. We let T1 star until T large K star to be equally spaced quantiles of the order distinct time points, which we later consider as grid points over time that serves as the restriction time points. VIK star becomes the stat restriction time-dependent covariates for subject I at time TK star, including 1 for the intercept. Then the restructured data consists of YIK star and VIK star, where YIK star is the minimum of TI, the observed survival time, and the TK star that we treated as the restriction time point. Adopting the IPCW and GE approach, we get this final form. I'm not getting into the details, but let me just point out one term here, which is now the weight function, WIK star, which now incorporates the IPCW accounting for the fact that TK star is now treated as the restriction time point. So we're comparing our observed survival time with the restriction time point TK star to construct this weight function. We've also adopted some ensemble-based approach with the purpose to reduce variance and to prevent overfitting. Let SB be a collection of large B mutually exclusive subsamples from the restructured data set. And given SB, we solve the following estimating equation. And for B equal to 1 until large B, we aggregate an ensemble of the estimators by taking the average of the estimated functions of betas and later derive the final form of beta tilde tau. In our simulation, we generated baseline covariates x1, x2, x3, all three generated from standard normal distribution. The treatment indicator Z was sampled from a Bernoulli distribution with probability written out like this, with alpha specified at 0.1 and 0.5s. The survival time was generated from a piecewise exponential model intentionally to let the covariate effects to vary across time. Censoring time was generated from a uniform distribution, 0 and tau C, where tau C could be selected to satisfy 30% and 50% of censoring rate. For each setting, we generated 500 data set with sample size of n equal to 1,000, and we compare the following models. The proposed model with eta, the log link, based on a set of fractional polynomials to model the time-varying treatment effects using single estimation. And we also apply the proposed method with the ensemble-based estimation. And lastly, we compare our proposed method with Tian et al.'s method. But unfortunately, we cannot directly use Tian et al.'s method because we still have this problem of heterogeneous population of patients. Hence, we extended Tian et al.'s model to adjust for propensity score with a prefixed tau. Just to give you an idea of the difference between our proposed methods and the TN's model, once again, is the fact that under our proposed model, we allow the covariate effect or the treatment effect to vary across time, and we're estimating the entire function of time for the treatment effect, whereas Tian et al.'s prefix a specific time point tau and estimate the covariate effect at that single time point. This is the simulation results. Overall, all three methods provides us with an unbiased estimate. The standard deviation and standard errors are all close to one another, and the coverage probability for the proposed method is close to the nominal level of 95%. When we increase our censoring rate to 50%, we see similar results. I just want to point out that for some propensity score estimation under Tian et al., we're seeing some bias. Now here's the summary of the simulation results. The proposed model using single and ensemble-based estimation both present unbiased estimate. The ensemble-based estimation does not improve variance estimation substantially, which was surprising and different from what we were expecting to see. Compared to Tian et al., the proposed model has smaller bias with comparable variance. So although we are estimating the entire function of time, Tian et al.'s performance and our proposed method's performance were pretty similar to one another. We applied our method to real data example to the inflammatory breast cancer data from the National Cancer Database. The purpose of the study was to assess the impact of trimodality treatment used on survival for patients with IBC. The study consisted of 10,000 patients who underwent surgery for non-metastatic IBC from 1998 to 2010. Among them, the annual percentage of trimodality therapy recipients fluctuated from 58% to 73%. And the previous study has shown that the use of trimodality therapy was associated with age, type of treating, facility, geographic location, rural, urban setting, age at diagnosis, race, insurance status, educational level, income, and comorbidity scores. 5 and 10-year survival rates were highest among patients receiving trimodality compared with patients who received surgery plus chemo, surgery plus RT, or surgery alone. So use of trimodality therapy was a significant independent predictor of survival. Now, in our application, the purpose was to assess the impact of trimodality treatment used on survival for patients with IBC that possibly changes over time. So for the propensity score, we assumed the probability of receiving treatment was associated with baseline characteristics via logistic regression model. And in the RMSD model, we included an intercept, treatment, and the propensity score, and we adopted the log link. We considered a set of fractional polynomials to model the time-varying treatment effects, and we adopted the single estimation procedure because we noticed that the ensemble-based approach didn't improve variance estimation as we hoped. We also conducted the extended Tian et al. Model that adjusted for propensity scores to make comparison. This is the result of the data analysis. You can see that the black solid line is representing our proposed method's estimate. The red crosses are from the Tian et al.'s method, where it has been all separately estimated through a prefixed tau points across time. Please note that this beta tau, because we're using a log link, denotes the log ratio of RMST. So you can see that it is increasing until 90 months, and it starts to decrease slowly. The red crosses are very wiggly over time, while our proposed method gives a smooth trend over time.
You have about
Interpretation.
2 minutes. You have about like 1.5.
Sure, thank you. I'm almost done. So the summary of the application, the differences in the baseline characteristics of IBC patients across different treatments have been accounted for in our model. Proposed model presents the treatment effect as a function of time in a smooth curve. On the other hand, the extended Tian et al. Estimated at each prefixed time point, leading to non-smooth fluctuating estimate across time. And the use of trimodality therapy increases the RMST by a range of 1.06 to 1.3, demonstrating a beneficial effect on survival. As tau increases until approximately 90 months, the RMST ratio increases gradually, then slightly starts to decrease afterwards, but still remains greater than 1. So to conclude my talk, I just want to make some summary points. The proposed RMST model that allows the treatment effect to vary across time provides a better picture in understanding the dynamic trend. The extended propensity score method addresses the imbalance in the baseline characteristics between treatments and reduced potential bias. Some sensitivity analysis may need to be conducted to the set of fractional polynomials. And that's all I have for today. I'd like to share my co-author's name here, and thank you all for your attention.
Thanks for the nice presentation. Do we have any question from the audience? Okay, then I have a quick questions. So
Sure.
how would you decide the size of the ensemble to get the estimate?
when you say the size, is it how much
Yeah. How
yeah,
much?
we sample, I can't really remember, but I think we used the 20% of the sample and we repeated multiple times. But any suggestions or comments on the ensemble-based approach will be very helpful because this is a still ongoing project.
Okay. Thank you.
Thank you.
Okay, so now we have the last speaker. So third speaker is Professor HAEUN Moon. She's from Seoul National University. Now you can have your talk ready. Okay, thank you.
Okay. Thanks for inviting me to this session as a speaker, Professor Im. And today I'm going to introduce my latest work titled as Augmented Doubly Robust Post-Imputation Inference Framework for Proteomic Data. This is a joint work with my postdoc supervisors, Catherine Rother and Jing Lee, and my colleague Jin Hong at Carnegie Mellon University. So this project was motivated from some modern data set, which is characterized by high resolution at the expense of unexpected messiness. A typical example includes peptide abundance data and gene expression data, which can be represented by this kind of matrix, where each row represents each subject and each column represents the peptide abundance level or the gene expression level. The colored cell represents the level of expression or the abundance, and the gray colored cell represents the missingness. With this data set, the typical research procedure involves first we impute the data set because these columns are highly correlated. So we first impute the data set, and using this imputed data set, we go through a variable selection procedure. So there is some external response variable y, and we want to identify genes or peptide that is associated with such covariate like disease status. However, the issue in this problem is that if we use the imputed data as if it were the original data set, it will increase the number of false discoveries. The reason behind this phenomena is that if we cross-use the high-dimensional matrix for imputation, the signal of the important peptide will be lead into the peptide which has no association with the covariate. So the resulted the imputed data set does not accurately represent the association status anymore. So our research goal here is that we want to build some valid and efficient imputation framework that is applicable after we do an imputation. Here we go down to a little bit of details. This is here I want to focus on the peptide data set. Here these brown colored columns represent some low dimensional covariate. There's no missingness here, and it is represented by some covariate like disease conditions that we wanna investigate, and some other covariate like gender or BMI that we wanna control. And we wanna investigate this regression analysis where the Y response will be one of these columns, and we want to regress this on the low dimensional covariate. So we repeat this procedure for each column of the matrix, and we want to finally collect the p-values of each column, and we want to select the peptide who has the lowest p-values. Since there are some missingness, this simple linear regression procedure is not straightforward. And here are the approaches that is readily applicable. The first one is the plug-in method. In this approach, we use the imputed data set as if it were the original, and we know that this will increase many false discoveries. Another one is called the complete method, where we want to do an analysis based only on the observed data. Because we focus on one peptide, one column at a time, we simply ignore the missingness and exclude such rows from the analysis. This is a readily applicable method, but is less powerful because it ignores the potentially useful information about the intercorrelation structure between peptides. This is our proposal. From now on, I will drop the indexes for a peptide J for the peptide, and I'm going to consider a one fixed peptide. Here I introduce two more notations here. First one is UI, which represents the entire matrix data, which is the source of the high dimensional imputation. Another notation is CI, which is the label for the missingness, which is 1 if y is observed and 0 otherwise. This is the linear regression that we want to solve. Here, y is only observable for some of the data set. Our strategy is that we will construct some pseudo outcome that is fully computable from the observed data and substitute the original outcome with missingness with this pseudo outcome without missingness. Two Nissan's functions are used here. The first one is the outcome model, which is the mean outcome conditional on both the low dimensional covariate and other peptide data. So simply, this is the output of the high dimensional imputation model. Another one is a propensity score model. Here, the probability of being observed is modeled using the low dimensional covariate W. Here we only use we assume that this propensity score is reasonably approximated using the low dimensional covariate, which means that we assume MAR, missing at random assumption. It makes sense because the source of the missingness in peptide data is largely technical. So if we include something like batch effect or other processing step as a low dimensional covariate, and that it makes sense, we can reasonably approximate the probability of being observed. And now we want to construct the pseudo outcome here. The first one is the plug-in estimator, which is simply the output of the imputation model. And what is the second term? This is called the bias correction term. It's basically the estimator of the mean zero function. So it does not perturb the target value, but it adds some good properties to the pseudo outcome construction. This is called the second order Nissan's estimation error. Here, what I labeled as estimate pseudo outcome is the pseudo outcome that we just observed. And this oracle pseudo outcome is the one when the true Nissan's functions are available. So this difference between the two represent the estimation error originated from the Nissan's estimation procedure. And the conditional expectation of this value is represented by the multiplication of these two terms. The first term is the estimation of the imputation model, and second one is the estimation error of the propensity score model. So what's the meaning of that, this second order Nissan's estimation error? It means that if we have one of the Nissan's estimators are consistent, then we will have the consistency of our pseudo outcomes. Also, it means that the convergence rate of our pseudo outcome will be fast because the rate will become the multiplication of these two rates of each of the Nissan's estimation function. So in our main theorem, we assume that the multiplication of these two Nissan's estimation is less than a square root 10 convergence. Then we will have that the estimated regression coefficient will achieve a square root 10 consistency, and its asymptotic variance will not affected by the Nissan's estimation procedure. This is a nice property that we achieve by construction, because if we use a simple plug-in method to achieve the same property, we need a strong assumption that the estimated imputation model achieve less than a square root 10 convergence, which is not even achievable for the typical parametric imputation model. However, in peptide data set, since it's a high dimensional, we usually consider some flexible machine learning or non-parametric imputation algorithm. Then the convergence rate will be much slower. So the key of this procedure is that even though we use such a slow imputational model, if we use this framework, this algorithm has some built-in algorithm to boost the power to achieve a square root 10 consistency, even when each of the Nissan's functions are slow. So our framework has a close connection to the causal inference studies. In causal inference, we typically want to estimate the mean outcome, but only observe the conditional mean outcome, conditional on the treated sample. So it's basically identical to the missing data problem. AIPW estimator, proposed in 1999, is an estimator from the mean outcome. And its demand is very similar to our pseudo outcome. This is the pseudo outcome. This received a lot of attention after its first proposal. And our contribution to this work is that we extend this AIPW estimator to a regression problem, and also we prove that if we augment one of the Nissan's parameter with the high dimensional auxiliary data set, then we can have the reduced variance. For application, we want to pick some high dimensional imputation model. Our application uses the method based on the deep learning algorithm called the variational autoencoder. It inputs some high dimensional matrix data set and learns its low dimensional representation. And from this low dimensional representation, it retrieves the original high dimensional outcomes. VAEIT, proposed in 2022, extends this VAE to handle missingness, so it is appropriate for our applications. In simulation, we compare 6 methods. The first one is a full method with the method that is without missingness, so it actually gives the optimal power that is achievable in this setting. Complete method is the method that we ignore the missingness, multiple imputation, and DRW is the method that is similar to our proposed one, but without the high dimensional imputation model. DRUW is the proposed method, and plug-in method is the one that I explained earlier as simply plug in the imputed outcome. Here, as expected, if we use the plug-in method, the FDR is largely inflated. However, the other method controls FDR well, but in power, our proposed method, the RUW, achieves a nearly optimal power as represented by the full method, while other methods are not very powerful. This is the property that is obtained from the design that we boost the convergence rate of our pseudo response. We applied this procedure to the single cell data here. Here, our response Y is the peptide abundance data for each of the peptide data set, and we regress this data on 4 low dimensional covariates. The first one is the cell diameter, and the others, we also consider other cell-specific covariate here. The research question here is that we want to select peptide that is associated with the cell diameter because the large cell can be a cause of certain cell activities, and is the main interest in cell biology, that how can the cell phenotype which internal component of the cell material push the cell to achieve certain kind of cell phenotypes. So here we first check the MAR assumption here, and this picture depicts that this data set is reasonably approximated by the MAR missingness assumption. And this is the selection result. Here, the x-axis 0.9765 is the threshold that is applied to peptide missing rate, because single cell data set have typically a very large rate of missingness. If we want to do some reasonable selection, we need to certain kind of cutoff to focus on some peptide with some sufficient amount of observed data. So as expected, if we lower the threshold, we will have more discoveries, but we need to sacrifice the FDR. Here, the blue colored bar is the result from the plug-in method, and it clearly inflate FDR in all of these thresholds. And among other three methods, the proposed method, the RUW method, consistently provides the lowest FDR and the highest power, which is consistent as the simulation result and theory. So to summarize, proteomic data is a good source of cell information, but it contains many missing values. So typical approach of plugging in the missing value will result in the inflated FDR. So we can devise the imputed outcome using the doubly robust pseudo outcomes to maintain a good control of false positives and contribute to additional meaningful discoveries. And thank you for listening.
Okay, thank you for the nice presentation. So is there any question from the audience? No? Okay. So I really appreciate all three speakers for keeping the time for their presentation, because there are multiple sessions on a queue, so it was so important to stay on schedule. Okay, so now I think our session is over. So I would like to thank all three speakers for their excellent talks and the audience for joining the session. So now we are all set. Thank you.
Thank you.